Right now, NASA is working through the final preparations for Artemis II, the mission meant to send astronauts around the moon for the first time since Apollo. Inside the vehicle assembly building, teams are checking systems, replacing components, and trying to keep the schedule on track for the next launch opportunity. But while most of the attention is on the rocket itself, another issue may matter just as much. It is not a dramatic hardware failure, and it is not the kind of problem that is easy to see in a photo from the launch pad. Yet, if it becomes serious, it could narrow NASA's options and place even more pressure on a mission that already sits at the center of the Artemis program. So this is not only about whether Artemis II can fly, it is also about what could still stand in the way, even if the vehicle is technically ready. So let's take a closer look. And if you value clear, step-by-step space coverage without the noise, this is exactly the kind of story worth following closely. At the moment, the Artemis II rocket is inside NASA's Vehicle Assembly Building at the Kennedy Space Center Vehicle Assembly Building. Engineers moved it there after detecting an unexpected interruption in the helium system of the rocket's upper stage. Originally, the Space Launch System, often called SLS, and the Orion spacecraft had already been positioned at the launch pad at Launch Complex 39B. But when the helium flow issue appeared in the Interim Cryogenic Propulsion Stage, or ICPS, NASA decided to roll the entire stack back to the assembly building for closer inspections. That rollback took place on February 25th. Inside the building, teams now have full access to the internal components of the upper stage, something that is difficult to do while the rocket is standing on the launch pad. Current reports indicate that NASA is targeting no earlier than March 19th to roll the vehicle back out to the pad. If that schedule holds, engineers would still have time to prepare the rocket for a potential launch window in early April. However, the timeline remains tight. The current launch opportunity for Artemis II is expected to run from April 1st through April 6th. If the mission cannot launch during that period, the next window may not arrive until later in the month. To understand what NASA is dealing with, it helps to look more closely at the system where the problem appeared. The issue involves the Interim Cryogenic Propulsion Stage, usually shortened to ICPS. This is the upper stage of the Space Launch System rocket. An upper stage is the part of a rocket that performs the final pushes after the vehicle has already left the dense lower atmosphere. In the case of Artemis missions, the ICPS is responsible for placing the Orion spacecraft onto the trajectory that will send it toward the moon. In simple terms, after the lower stages lift the rocket away from Earth, the ICPS provides the final burst of energy that sends the spacecraft into deep space. The ICPS relies on a cryogenic propulsion system. Cryogenic means that the propellants are stored at extremely low temperatures. In this case, the stage uses liquid hydrogen and liquid oxygen. Liquid hydrogen must be kept at around minus 253 degrees Celsius, while liquid oxygen remains liquid at about minus 183 degrees Celsius. Because these propellants are so cold, the systems that control their flow must operate very precisely. Helium plays an important role in this process. It is not used as fuel, but as a pressurizing gas. Inside the stage, helium helps push propellants through pipes and into the engine. Without proper helium pressure, the fuel cannot flow correctly through the system. The interruption NASA detected involved the helium flow within this upper stage. Engineers observed that something in the system was preventing the helium from moving through the hardware as expected. When this happens, the rocket cannot simply proceed toward launch because the propulsion stage would not be operating within its required safety limits. Investigating the problem requires examining several possible components. One potential source is a final filter located between the ground support systems and the rocket itself. Filters are used in fluid systems to prevent small particles from entering sensitive hardware. Even a tiny obstruction could affect how gases move through the lines. Another possible source is the quick disconnect interface. This is the connection point where ground equipment attaches to the rocket while it is on the launch pad. Through this interface, technicians supply propellants, gases, and other resources to the vehicle before liftoff. When the rocket launches, the connection separates in a controlled way. If a seal inside this interface becomes damaged or worn, it can interfere with fluid flow. A third candidate is a check valve inside the ICPS. A check valve is designed to allow gas or liquid to move in only one direction. Its purpose is to prevent backflow, which could disrupt the propulsion system. If a check valve sticks or fails to seal correctly, it can change the pressure conditions inside the stage. Interestingly, a similar component had already caused trouble during the earlier Artemis I mission. After that flight, NASA implemented modifications intended to reduce the likelihood of the same issue happening again. But complex systems can still produce unexpected behavior, especially when multiple components interact. Because the suspected hardware is located inside the upper stage, engineers cannot easily access it when the rocket is standing vertically at the launch pad. The launch pad allows technicians to reach the boosters and some external systems, but internal access to the upper stage is extremely limited. That is why NASA decided to roll the entire rocket back to the vehicle assembly building. Inside this facility, the rocket can be serviced with specialized platforms and equipment that allow technicians to reach internal components safely. Once inside the building, engineers can remove the suspect parts and inspect them directly. The goal is not simply to fix the immediate problem, but to determine the root cause. In engineering, identifying the root cause is critical. If the investigation only addresses the symptom, the same issue could appear again during later operations. While the rocket remains in the assembly building, teams are also taking the opportunity to perform additional maintenance and testing tasks. For example, they are replacing batteries in the flight termination system, often abbreviated as FTS. This system is a safety feature used by range authorities. If a rocket were to veer off its intended flight path, the system allows controllers to safely destroy the vehicle before it could threaten populated areas. The batteries in this system must meet strict certification requirements before a launch can proceed. Replacing them while the rocket is already inside the building is more efficient than doing the work later at the pad. Engineers are also performing a full end-to-end systems test. This type of test verifies that all the rocket systems communicate correctly with each other and with ground control systems. Another task involves the tail service mast umbilical, which is part of the fueling infrastructure at the launch pad. Umbilicals are connection systems that feed propellants, gases, and electrical power into the rocket before launch. In this case, technicians are replacing a seal associated with the liquid oxygen supply line. Even though there were no confirmed leaks in that particular system, NASA previously replaced similar seals for the liquid hydrogen lines during earlier testing. Performing the replacement now adds another layer of precaution. Meanwhile, teams working with the Orion spacecraft are reviewing the hardware and equipment stored inside the crew module. The closeout crew, the technicians responsible for sealing the spacecraft before launch, are also practicing their procedures again. All of these tasks are happening while engineers continue the central investigation into the helium system issue. At first glance, the issue with the helium system might seem like a relatively small technical delay. Rockets are complex machines, and troubleshooting hardware before launch is a normal part of spaceflight operations. But Artemis II is not just another launch. It sits at a critical point in the timeline of the entire Artemis program. Artemis II is designed to be the first crewed mission of the new lunar exploration effort. 4 astronauts will travel aboard the Orion spacecraft, launched by the Space Launch System, and fly on a trajectory that takes them around the moon before returning to Earth. The mission is primarily a test flight, but it carries major significance. If Artemis II flies successfully, it would demonstrate that the Orion spacecraft, its life support systems, and the SLS launch vehicle can safely carry astronauts into deep space. That demonstration is necessary before NASA can move forward with missions that attempt to land astronauts on the lunar surface again. Because of this, Artemis II effectively sets the pace for everything that follows. If the mission launches on schedule and performs as expected, the next missions could continue moving forward according to NASA's current roadmap. Artemis III, for example, is intended to test additional systems and capabilities that will eventually support human landings near the lunar South Pole. However, if Artemis II experiences a significant delay, the effects could extend far beyond this single mission. Launch schedules for deep space missions are often tightly connected. A change in one mission can shift the planning for the next several flights. For example, NASA has indicated that the Artemis III mission may focus on testing systems in low Earth orbit before attempting a lunar landing. If that plan remains in place, the first new human landing on the Moon could occur during Artemis IV instead. If confirmed, that would move the timeline for the next lunar landing closer to the end of the decade. At the same time, other nations are continuing to develop their own lunar exploration programs. China, for instance, is preparing the Chang'e 7 mission, which is expected to explore the region around Shackleton Crater, near the Moon's south pole. That region is receiving attention because scientists believe it may contain deposits of water ice trapped in permanently shadowed areas. These are locations where sunlight never reaches the surface, allowing extremely cold temperatures to preserve frozen materials. Water ice is important because it could eventually support long-term lunar exploration. If astronauts can extract water from lunar soil, it could potentially be used for drinking water, breathable oxygen, or even rocket propellant. To support the Chang'e 7 mission, researchers have developed new models predicting where water ice is most likely to be found in the Shackleton region. These models combine data from lunar orbiters with simulations of how sunlight, radiation, and internal heat affect temperatures across the surface. The Chang'e 7 spacecraft itself is planned as a multi-element mission. It includes an orbiter, a lander, rovers, and a small hopping probe designed to move in and out of permanently shadowed craters. These robots will drill into the lunar soil, heat the samples, and analyze the released gases to detect water molecules and other chemicals. If missions like Chang'e 7 succeed, they could provide valuable data about the distribution of ice at the lunar South Pole. That information would be important for any future plan to establish long-term operations on the Moon. So while the technical issue affecting Artemis II is being addressed inside NASA's assembly building, the broader effort to explore and eventually utilize the Moon continues to move forward around the world. For now, several key questions remain unresolved. The most immediate one is the exact cause of the helium flow interruption inside the interim cryogenic propulsion stage. Engineers are still inspecting the suspect hardware, and until that process is complete, NASA cannot fully confirm whether the issue came from a filter, a quick disconnect seal, a check valve, or another part of the system. Even after the root cause is identified, the teams must verify that the fix works reliably. That typically involves inspections, replacement of components if needed, and additional system tests to ensure the propulsion stage behaves normally during operations. Another uncertainty involves the launch schedule. NASA is currently aiming to roll the Space Launch System rocket back out to Launch Complex 39B around March 19th. If that rollout happens on time, teams would still have roughly a week and a half to complete final preparations before the earliest launch opportunity. The current launch window for Artemis II is expected to run from April 1st through April 6th. If the rocket is not ready by then, the next opportunity could shift to April 30th or later. Because lunar trajectories depend on precise orbital alignment between Earth and the Moon, missing one window can sometimes lead to longer gaps before the next available opportunity. There is also the broader question raised by the solar physics research. Scientists studying solar activity suggest that the Sun may currently be in a period of increased superflare potential. If confirmed, that could raise concerns about radiation exposure for astronauts traveling beyond Earth's magnetic field. Whether that research ultimately influences launch planning remains unclear. NASA typically relies on continuous space weather monitoring and mission-specific risk assessments when making final decisions about crewed launches. For now, the most important milestones to watch are straightforward. First, the completion of the hardware inspection inside the vehicle assembly building. Second, the rollout of the rocket back to the launch pad. And finally, the readiness reviews that determine whether Artemis II can proceed into its next launch window. As those steps unfold, they will not only determine when Artemis II flies, but also how quickly the next phase of lunar exploration can move forward. And as new updates appear, they may reveal how this mission continues to shape the direction of human exploration beyond Earth.